Hi, this is an example problem on interstellar space travel from Chapter 28 on special relativity. Pause for a moment and read the question. All right, so previously I had a video on a muon that was traveling, and there were two different reference frames, the Earth and the muon. This problem is very similar. Instead of a muon traveling, we have a person in a spacecraft traveling, and there's two different reference frames. One for the Earth observer and a second for the reference frame of the rocket, the person in the rocket. Now, when we read this question, it doesn't tell us, but the assumption is that Capella is at rest with respect to the Earth and, of course, with the observer on the Earth. So Earth, Capella, the Earth observer, they're all in the Earth's reference frame. Because of that, the distance L0 between them, these 2 points are not moving in the Earth's reference frame, so that is your proper length between Earth and Capella. And so let's go ahead and divide this up here so we can label the values for time, interval, distance between objects in the two reference frames. So a space probe is sent to the vicinity of the star Capella, which is 42.2 light years from Earth. And that is by assumption measured in the Earth's reference frame. Part of the reason why I'm doing this problem is so we can get used to a new type of unit for distance, which is light years. So when I say the length measured in the Earth reference frame between Earth and Capella, we said that's the proper length L0. It's equal to 42.2 light years. And light years is a unit of distance. So let me show you something real quick here. Light year is the distance that light travels in 1 year. We know light travels at the speed c, 3 times 10 to the 8th meters per second. More digits of precision there. Multiply that by a year, and you're going to come up with 9.46, etc., times 10 to the 15th meters. That is 1 light year. That's what a light year is equal to. That's a conversion factor between light years and meters. It's really useful to use light years when you use a time in the units of years, because the speed of light normally we think of as 10.8 meters per second. Now the speed of light, well, light travels 1 light year, right? The distance light travels 1 year per year. So the speed of light is just 1 in units of light years per year. So that makes some things easy here. So we are asked in this case, right? So the probe travels with a speed of 0.991 c. Well, that means that this speed is 0.991 light years per year. I think I'll just call years y. It says an astronaut recruit on board is 19 years old when the probe leaves Earth. What is her biological age when the probe reaches Capella? So we want to know what delta t is, right? So the two events here we're talking about are, the first event, rocket leaves Earth. And event 2 is rocket reaches Capella. In the rocket reference frame, you have the same two events, but from this point of view, right, this rocket person is like going to say, I'm at rest in my reference frame, right? And it's the Earth and the stars that are moving. Well, because the two locations where the Earth and the star are at in their reference frame, they're moving. That means this is a contracted length. However, the position of the start and stop of the timing of these two events occur at the same place for the observer in the rocket ship. Both of these events occur at the same place, since the rocket person is just sitting there, and first the Earth is at their origin, x equals 0 for them, and then later on the star arrives there from their perspective. So they're going to have a contracted length, but they will measure the proper time. Whereas the Earth observer, delta t here, the two events from their point of view, one is at the Earth, one is way over Capella, two different points in space from their point of view. That means that that's going to be a dilated time. So now to answer the question, what is the space traveler's biological age when she reaches Capella? Well, to measure her biological age, you need to use a clock that is on her spacecraft, because she ages at the rate biologically that a clock does. In other words, if you're an Earth observer and you notice her clock slow down, well, her aging will also slow down. So we need to figure out what delta t0 is. There's a couple ways to do this problem. I could use the equation speed is equal to distance, L, divided by time, delta t0. And we know what we need to know what V and L are. So one way to do that is to use a gamma factor and to convert between these two. So let's try that way of doing it real quick here. So let me compute gamma in this problem. Gamma is equal to 1 divided by square root of 1 minus 0.991 c divided by c. C's cancel, and when we put this into the calculator, we get a value equal to about 7.47. So if I want to calculate what the dilated length is of the distance between Earth and the star as observed or measured by the space traveler, it's going to be the proper length divided by gamma. Proper length, okay, that's from the Earth's measurement, 42.2 light years, divided by gamma, 7.47, which comes out to a value equal to 5.65 years. So now we can go ahead and solve for the time, delta t0, from the simple constant speed equation. That means that it's going to be length divided by speed. Again, I'm only using the length and time intervals, right, for the rocket reference frame. That's going to be 5.65 years divided by 0.991 light years per year. And I think I have a mistake here. I do. This is a distance. It's light years. Okay, so that fixes that. Now we can cancel the light years. And the 1 divided by 1 over years becomes years. And this comes out to 5.7 years. Right, so by noticing how fast the Earth and the star Capella are traveling and looking at the distance, you can calculate the time just in the same reference frame for the rocket. So according to that, the person in the rocket has aged 5.7 years. And so to answer the question, what is her biological age? Well, her biological age, she started out at 19 years, right? So we're getting rid of the R here. And then the trip took 5.7 years on her clock. So she is an age of 24.7 years. And that's our answer. Now, I want to show you another way to do this, which will demonstrate that for the Earth observer, more time has elapsed. So let's use the speed equation, constant speed, in the Earth observer's reference frame. And we'll be able to calculate what the time is. So for the Earth observer, the speed v, that's the distance L0, divided by the time delta t. We want to calculate delta t here. How long does it take for the space ship to travel? Well, we know how far it's got to go, L0, and we know how fast the Earth observer sees it going, 0.991 light years per year. So the time interval is going to be that distance divided by the speed. That is 42.2 light years divided by 0.991 light years per year. The light years will cancel, and we'll come up with a time. So the time that has passed on Earth now, it's going to be equal to 42.6 years. 42.6 years have elapsed according to the Earth observer between the same two events, which for the rocket observer are 5.7 years. So let's just go ahead and confirm that this is correct by using the gamma factor to convert. So if we do that, to convert from the dilated time and the proper time, right? So we want to calculate the proper time. In this case, delta t0 is equal to the dilated time divided by gamma. Dilated time from the Earth observer's measurement, 42.6 years, divided by gamma, 7.47. We do that calculation, and it comes out to the exact same thing, 5.7 years. So as you can see, there's more than one method to calculate these problems. And much more interestingly, we see that time dilation can create some really strange effects. Now, we don't have the ability to travel that fast, but if this were possible, you could do something which is known as the twin paradox. If this person were to turn around and come back, well, by symmetry, it would take them another 5.7 years according to their clocks inside the space shuttle. On Earth, another 42.6 years would pass. So you could have someone who is traveling at a very young age with their twin state on Earth. When they come back, they've only aged about 12 years. Their twin on Earth is going to be an elderly person at that point. And so this is all a very strange thing that we might want to say this is not real, it's not possible. But in fact, actually, this is all consistent with relativity. And if we were able to have the energy to do such an experiment, this is exactly what would happen.